video is going to be on classification of matter, which is always pretty much the first thing that you learn in any general chemistry course. And so before we start talking about classifying matter, we should define it. And so matter is anything that has mass and occupies space. And so most of the things that we'll talk about in a chemistry class over the course of the year qualify as matter. The main thing that isn't matter that we'll spend a lot of time talking about in class this year is energy, but that's not a topic that we're going to get to just yet. And there are various ways that we can classify matter. One would be by physical state. So for example, and there are three major physical states that we'll talk about: gas, liquid, and solid. So a gas is a physical state in which the particles are not in constant contact with each other, and it's compressible. A liquid would be a state of matter in which particles of the substance are in constant contact with each other, but they have the freedom to move around relative to each other, and that would be non-compressible. And then a solid, in which the particles of the substance are in constant contact with each other, and then they're fixed in a sort of lattice or array, and that's also a non-compressible state of matter. Now, having said all that, that's actually not the classification of matter that we're talking about today, but it is something that we will get back to a little bit later in the year. What we want to do in this video is talk about classifying matter using terms like substance and element, compound, mixtures, a heterogeneous mixture, and a homogeneous mixture. So the way your book does this is has a sort of logic tree in which you would use this logic tree to sort of interrogate various samples of matter and then use that to decide how to classify them. So we'll go through the tree that your book has, and then we'll go through some definitions of some of these things, and then look at it. There are various ways of thinking about this, and so we'll look at a second sort of logic tree later on. So here's the logic tree that's in your textbook, and it starts with any sample of matter. And so just for the purpose of going through this, I've thought about three things we can compare. So let's think about a chocolate chip cookie, a glass of water, and a glass of sweet tea. And so two people sit down that they're going to eat chocolate chip cookies. One of them is going to drink water, and the other one's going to drink sweet tea. Well, the cookie, the water, and the sweet tea are all examples of matter. And so now we're going to ask a first question, which is that sample of matter uniform throughout? And so given our three samples, let's think about them. The chocolate chip cookie is not uniform throughout, right? Because it, in some places, it has chocolate chips, and other places it doesn't. And if we were to look at it through a microscope, we could see that even in just looking at the part that doesn't have, that's totally not chocolate chips, we could still see there's some parts that had pockets of air and some parts that had little bits of flour and other bits of this and that. So it doesn't have a uniform composition. And really what we would define a uniform composition is that no matter how large or small a sample you take of that sample of matter, and no matter where you take it, that you would always get the same thing. And that's not true with a chocolate chip cookie. Depending on how large or small the sample is, or where in the cookie you sample it, you'll get different things. And so if the answer to that question is no, for example, with the cookie, it is not uniform throughout, then that we would define that as a heterogeneous mixture. So cookie, classic example of a heterogeneous mixture. Well, both the water and the sweet tea are uniform throughout. So if I take a glass of water, and no matter where I sample it in that glass, no matter how large or small the sample is, I'm always going to get the same thing. I'm just going to get water, and it's going to be a compound that's got made up of hydrogen and oxygen, always in a mass ratio of 89% oxygen to 11% hydrogen, or 2 hydrogen atoms to every 1 oxygen atom. It's homogeneous. It's going to be uniform. The sweet tea is also uniform. That is to say, no matter how large or how small a sample I take within that glass, and no matter where in the glass I sample it, because it's very thoroughly mixed, I'm going to get that same, I will always get the same ratio of water to sugar to caffeine to flavoring uh, substances. It's always going to give me a uniform distribution of those things. So both the water and the sweet tea are homogeneous. How they differ is in the question of, does it have a variable composition? And so that would seem like a confusing thing to ask. If a thing's got a uniform composition, how can a thing have a uniform composition but have a variable composition? Well, let's think for just a second. Let's step back away from the water and the sweet tea for just a second and just think about just thinking about a solution of sugar in water. So I take uh, 5 grams of sugar and I dissolve it in a gallon of water and I mix it up thoroughly. And I've got a solution that has a uniform composition. No matter where I sample that, I'm going to get the same ratio of sugar to water because it's thoroughly and homogeneously mixed. But now I can come along and make another solution in which I put 10 grams of sugar into a gallon of water and mix that up and dissolve it. It's also homogeneous. It also has a uniform composition. But one of them has 5 grams of water per gallon, 5 grams of sugar per gallon. The other one has 10 grams of sugar per gallon. So they have a variable composition. Within each sample, it has a uniform composition, but but the two samples are different from each other. So that's what we mean by variable composition. I can make lots and lots of different variations on sugar water, each of which will have a uniform composition within itself, but will vary from the sample next door. And so that's what this question is asking. And so water, well, let's forget about the water for a second. Let's think about the sweet tea. Sweet tea does have a variable composition. I can come back the next time and make a sample of sweet tea that's got a little bit more tea and a little bit less sugar in it. It's still the same, all the same components, but I have varied the composition. So because sweet tea has a variable composition, we would say that that is a homogeneous mixture or a solution. The water, by contrast, does not have a variable composition. Any sample of water that I have, assuming that it's pure water, is going to have always the exact same composition. It's going to be made up of molecules that have 2 hydrogen atoms for every 1 oxygen atom, or 89 grams of oxygen for every 11 grams of hydrogen. It's always going to have the same. It's always going to have the same composition. And so water, the sweet tea is a homogeneous mixture. The water is a pure substance. Now, we can finally take a pure substance and we can interrogate it as to whether it can be separated into simpler substances by some chemical process. So now I'm going to have to introduce some other thing to compare water to. So let's compare water to oxygen gas. They're both pure substances. They are both things that they're homogeneous and don't have a variable composition. But water is made up of hydrogen atoms and oxygen atoms, whereas oxygen gas is only made up of oxygen atoms. And so oxygen gas cannot be separated into anything simpler. It's oxygen and that's that. Water actually can, by a chemical process of electrolysis, be separated into its component elements, hydrogen and oxygen. And so oxygen gas would be an element because it can't be separated into anything simpler. Water would be a compound because it can be separated using a chemical process into its constituent elements, hydrogen and oxygen. So let's go ahead and take some examples of things and run them through this logic here. So let's take an example of filtered seawater. I go down to the beach, I get some water out of the ocean, and I filter it so it's nice and clear and no particulate matter in it. It's just filtered seawater. So I've got that sample of matter. Is it uniform throughout? It is, because I filtered out any particles that might settle or float around, and it's just a uniform glass of seawater. And so that's a homogeneous sample of matter, that filtered seawater. Does it have a variable composition? Well, it does, because I could actually dilute that out with some more water and still have seawater that has all the same substances in it, but just now in different ratios. And so filtered seawater would, and we would stop here, would come down to being a homogeneous mixture. All right, let's say that I went down and I didn't filter my seawater and I'd scooped up some sand along with my seawater. Now, again, I've got that sample of matter, and so is it uniform throughout? It's not. It's got little particles of sand in it, and it's particularly obvious that if I just let it settle, that I'm going to have a big pile of sand on the bottom and not at the top. So it's not uniform throughout. And therefore, this seawater and sand would be a heterogeneous mixture. The terms heterogeneous and homogeneous literally from the Greek mean of a different type and of the same type. And so, and it really just means, is it uniform? So a homogeneous substance is uniform throughout. A heterogeneous mixture is not. Okay, on to a third thing, acetone. Acetone is an industrial solvent. It's also used in nail polish remover. And it has this formula of C3H6O. Here's a little picture of a bottle of acetone. So I've got my sample of acetone. Is it uniform throughout? It is. It's a clear liquid. Everywhere I sample it in there, I'm just going to get this acetone, which has the same composition, C3H6O. So that is a homogeneous sample of matter because it is uniform throughout. Does it have a variable composition? Well, acetone is acetone, and no matter where because there's only one thing in that bottle, acetone, and it's always going to have the same formula no matter where I sample it, then that does not have a variable composition. It is a pure substance. Acetone is an example of a pure substance. Could it be separated into simpler substances? Well, I've sort of tipped you there by giving you a chemical formula. It can. It is possible through a series of chemical reactions to break down acetone into pure carbon, pure hydrogen, and pure oxygen. And so because the answer to that question is yes, then acetone now is defined as a compound. And then the last example we'll look at here would be helium, not the balloon, but the helium inside. Again, I've got a sample of matter. Is it uniform throughout? It is. No matter where I sample that, I'm just getting helium. So it's homogeneous. Does it have a variable composition? It doesn't, because it's made up simply of helium. I can't vary its composition. So it's a pure substance. Can it be separated into simpler substances? It cannot. It is made up strictly of helium atoms. And so therefore, it is an element. So that's how you would use the logic tree that's in your textbook. Let's now do this a slightly different way, which is to start by defining some things. So I'm going to go back to the slide that I had that had some words on it, and now we're going to give some terms on it, and now we're going to give some definitions to some of those terms. So a substance would be defined as a sample of matter that has a definite composition and fixed properties. And so water fits this description because it has that that definite composition of H2O, and it has fixed properties. Pure water has a fixed boiling point, a fixed melting point. At a given temperature, it has a constant density. It will always react in the same way with certain things. It will always dissolve certain substances and not others. So it has a fixed composition. It has a definite composition. It has fixed properties. Acetone the same way. It is always going to be C3H6O. It's always going to have a certain boiling point and melting point. By contrast, sweet tea, even though it's homogeneous, it is not pure because I can vary its composition. I can vary the amount of sugar and water in tea, and that will change its properties. That will change its density. That will change its flavor. That might change its color. Within substances, I can define an element as a substance that consists of only one type of atom. Couldn't say element, that's kind of redundant. Element consists of one type of element. A substance containing only one type of atom, and so it can't be separated into simpler components. And so helium would be our example that we looked at before. Helium is made up strictly of helium atoms, and so it is an element and it can't be separated into anything simpler. A compound is a substance that consists of two or more types of atoms, and so water and acetone would be examples of that. Water is a pure substance consisting of hydrogen and oxygen. Acetone is a pure substance consisting of carbon, hydrogen, and oxygen. A mixture then is going to be a sample of matter that simply consists of two or more different substances. And so sugar water consists of sucrose, which is one pure substance, and water, which is another, mixed together. Sweet tea consists of water and sucrose and caffeine and different coloring and flavoring substances that come out of the tea leaves. So those would be mixtures. A cookie is a mixture of chocolate and milk and flour and butter and eggs and things like that. Within mixtures, a homogeneous mixture is a mixture that has a uniform composition. So again, the sweet tea is a mixture that is uniform. No matter where I sample it in the glass, it's going to have the same composition as somewhere else in the glass. A heterogeneous mixture has a non-uniform composition. The cookie, the salad dressing, if I sample these in different places, I will get different compositions. So here's a way of looking at this that comes from a different textbook. And in this case, we're starting with matter. And we're saying matter is either going to be, a sample of matter is either going to be a mixture or a pure substance. And so in this case, we can define, again, we can go back and just define a pure substance as something with a definite composition and properties. But another way to think about this is, could I break that sample of matter down into simpler components by some physical process? And so let's, in that case, compare, let's compare seawater with sand in it to pure water. Can I separate that seawater with sand into simpler substances by a physical process? And the answer is yes. I could get rid of the sand by filtering it. And then once I had that seawater left, that filtered seawater, I could actually separate that by boiling the water off and leaving all the salt behind. And so these are physical processes, filtering, boiling, heating, cooling, that I can use to separate something into simpler substances. And so seawater can be separated into simpler substances using physical processes. Water, acetone cannot. If I heat them, if I cool them, if I freeze them, if I boil them, the one is still water, the other is still acetone, so it's a pure substance. If I can, then it's a mixture. And so again, within mixtures, there are two types of mixtures. A heterogeneous mixture, which has a non-uniform composition, cement, salad dressing, cookie, things like that. A homogeneous mixture, Gatorade, Kool-Aid, air, sugar water, sweet tea, has a uniform composition. Within substances, I can define them as either elements or compounds. And one way to look at it is it made up of more than one type of atom? Yes, it's a compound. If not, it's an element. But the other way to ask this is, could I break it down into simpler substances by a chemical reaction? Water, yes, I can break it down into hydrogen and oxygen. Acetone, yes, I can break it down into carbon, hydrogen, and oxygen. Oxygen gas, no, I can't break it down into anything simpler. Neon gas, no, I can't break it down into anything simpler. Let's just finally take a look at some pictures of things and try and see what we're talking about at the sort of particle level. So we've got substances A, B, and C. And so if I was going to ask you, is this a picture of an element? Is it a picture of a compound? Is it a picture of a mixture? Which would you choose for each of these? And you could pause if you like and take a look at these and then turn the video back on. Okay, well, A, as you can see, is made up of only one type of atom. And so the idea here is that a given type of atom has a fixed color. And so because A is made up of only one type of atom, that would be an element. And in fact, this is probably intended to be like helium or neon, which are what are called monatomic gases. B, you can see, is made up of more than one type of element. In fact, in the convention for molecular modeling, black is carbon and red is oxygen, and so these would be carbon dioxide molecules. But what you'll notice is that it's all the same. Everything that's in there is a carbon dioxide molecule. And so B is an example of a compound, pure substance. All these molecules are identical to each other, but they're made up of more than one type of atom. And so B would be a compound. C, you can see, is made up of two different types of elements, a green one and an orange one, but also the fact that there are some particles that are only green, contain two atoms. I think it's probably chlorine. And then there are some particles that are only orange. And so that would be a mixture of the green particles and a mixture of the orange particles. And you'll notice that the artist here has sort of taken care to show that these things are pretty much distributed evenly throughout. And so I think they're trying to suggest a uniform composition here. The C would be a mixture, and I would even go so far as to say that they're trying to portray that as homogeneous mixture because it has a uniform composition. Okay, that's the end of the video. So go ahead and take a look at what problems are assigned to go along with this, and we will see you next time.